Welcome to part 2 of our chapter 19 discussion. We were talking about branch circuits when we left off, and we're going to continue that discussion for the next few slides. So the branch circuit rating is determined by the rating of the overcurrent protection device. That's just another way of saying that the circuit itself cannot exceed the overload protection that it's connected to, namely the circuit breaker. So if you have, for example, a 20 amp circuit breaker that you're running a number of things off of, lighting, outlets, and so forth, the combined total amperage that we're going to draw off that circuit should be estimated based on the likelihood of the things we're going to have plugged into it. So the connected load on a branch circuit is the sum of all the loads connected to it. And we figure that out basically by calculating all of the things that are going to be connected by wattage or voltamps. So the question might be, well, how do we figure out the wattage? Well, we can look up specific wattage of all the individual devices that we're plugging into our circuit. And that includes light bulbs, refrigerators, vacuum cleaners, all of these things that we draw electricity with. And then just add up all those wattages. Remember the relationship between watts and amps and volts. For example, if we add up all the wattages of all the devices and it comes to 1,000, how do we know how many amps that circuit needs to be? Well, basically we're just going to take that 1,000 watts and divide it by the voltage to get the amperage. So let's say we have 1,000 watts on a circuit. We divide that by the voltage, 120 usually, equals 8.33 amps. So we know that in this scenario, really any breaker that you can buy for a residential application is going to be capable of servicing that circuit. Generally, in a residential application, breakers, the smallest one you're going to have is a 15 amp breaker. But then you might also have a 20 amp breaker, and in some cases, if it's a much higher draw, a 30 amp breaker. So how do we figure out that total? How do we know what all of the combined wattages or voltamps are going to be on a given circuit? There are tables, such as this one, that describe the expected load, and it's just sort of a range really, but they're sort of taking an average of the various things that are available. Really the best way to do it is to look at the specific appliance, if you know what it is, that you're going to be plugging in, or maybe it's a permanently connected appliance. But in the absence of that specific information, there are tables available like this one that can give you sort of the standard connected loads based on the type of appliance that it is. If we continue on looking at the next slide, you can see there's some additional guidance on that for other types of devices, and even more on table 1914, and yet more on table 1915. So you can see that there's a lot of sort of available information, keeping in mind that a lot of this stuff is coming down as electronics get more advanced, and we have the sort of widespread adoption of LED lights over incandescent and fluorescent. The power draw is coming down dramatically. So just be aware that if you are looking at a table for guidance, you may end up oversizing a circuit unnecessarily and just sort of leaving a little bit of money on the table that way. In other words, just make sure the tables you're looking at are current and sort of well aligned with modern appliances. And of course, there's one more table, 1916 here, that shows some additional equipment. Now I'm going to go back a few slides because I jumped over a couple just to kind of answer that question I posed. Table 1911 shows us the maximum connected loads, voltages, and requirements for a common 120 volt residential circuit. And this table is pointing out the circuit protection, the overload protection listed on the left here. You can see that the overcurrent protection corresponds with that amperage rating. But this is breaking down the maximum 100% connected load in volt amps or watts. And then there's also a separate column that's slightly smaller, and it says the maximum continuous load, 80% of the connected load. So presumably this is talking about a system where, or the device where it's sort of always on, like a heater or something like that. It's going to be on for an extended period of time, or maybe even always, like a pump motor or something like that. So we need to make sure that we don't exceed 80% of the connected load in that situation. But for things that are just intermittent, like receptacles that you might plug a vacuum cleaner or a lamp into, the maximum connected load would be 100%. So where this 1800 comes from, this 2400, we're basically just taking the amperage available multiplied by the voltage that is running it. And as you see, that voltage isn't listed here, but we see it down here in the heading 120 volts. So 15 times 120 equals 1800, so forth and so on. So these next few slides are just going to take a slower walk through the various branch circuit types that we talked about at the beginning of this section. The general purpose circuits, as mentioned before, are going to feed more than one outlet. So these are just the normal receptacles that we see in our walls in a residential or commercial structure. And multiple outlets are going to be fed by the same circuit. So we could expect to, the more things we plug in, the more draw that's going to be pulled from that circuit. And we try to design the number of outlets or receptacles that we put on a circuit with the expected load that would be applied to those outlets at any given time. For example, you might estimate that, okay, one outlet might have a lamp plugged into it, and another one on that same circuit might occasionally get a vacuum cleaner plugged into it or something like that. In a kitchen, obviously, you're going to have a much higher draw, so the number of outlets that we connect on a circuit in a kitchen is lower than what we might put in a living room, for example. In a kitchen, it wouldn't be uncommon to be running a microwave and a toaster, for example, at the same time. So obviously that draw is going to be much greater than an LED light bulb and, say, even a vacuum cleaner. An individual circuit is what we typically would associate with like a clothes dryer or some other piece of equipment like a range or an oven that is going to be kind of a heavier draw. We don't really want, well, we can't have anything else on that circuit. It needs to be dedicated. And it says here that any equipment rated above 25 amps must be placed on a separate individual circuit because of the 50% maximum single load limitation. So really, if it's below 25 amps, so if it's a 20 amp, typically that's going to be a general purpose circuit. We don't typically have that low of a draw on a dedicated piece of equipment. They're generally things that are going to be pulling a lot more electricity. So this slide is just showing sort of a description of what a general purpose circuit might look like, combined with a couple other things. So we have three different circuits shown here. You can see one is a dedicated circuit that's going to be running an air conditioner or window air conditioner unit. And so we just basically have a single wire going or cable going from the breaker box over to that outlet. And you can sort of see that each one of these arrows is just indicating that from that point we're going all the way back to the panel. We're going to be feeding that particular location directly off of a panel with a single cable coming in. We have a single lighting circuit, so not really sure why they're showing this one light kind of going back to the panel all by itself. Typically we're going to be running multiple lights on a single circuit, unless that's just some sort of special light. Maybe it's a grow light or something like that with a huge draw. I don't know. And then down at the bottom here we have these general purpose outlets all connected to each other and going back to the panel from this one right here. Down below, this is kind of what that looks like in an electrical plan view. So this is kind of how we show those things associated with each other. Each point that we're sort of at the end of the circuit, like this dedicated outlet here, just going to show a little arrow coming off of it, and that's just indicating that we're running that back to the panel. Same thing as what we're seeing up here in the 3D. In this scenario, we're showing how we're typically going to wire a multiple light system. In this case, we have a single circuit serving 2 rooms. Each room has 6 lights in it. And the way that typically works, and the way we're going to typically show this on a plan, is we're going to be, in this case, we have a junction box, a separate junction box that is going to receive the power from the panel. And then from that, it's going to split out to 2 separate switches. So we're going to run those cables into the switch box, and then from there, we'll put the switch in line and then extend that out of the box up to the lights themselves, and each light will be connected in sequence as shown. Lights are typically installed in parallel. Remember the discussion between parallel and series. Parallel means that each light has its own connection, both positive and hot and neutral, so that if one light burns out, the others are not affected. Appliance circuits are similar to general use circuits, except that we're going to limit the number of those that we have. So this would apply to a kitchen, for example. Generally, these are going to things like refrigerators, washers, and other kind of larger appliances that we typically don't unplug, even microwave ovens, things like that, that are just sort of permanently plugged in all the time. That would be an appliance circuit. And appliance circuits cannot exceed 20 amps, so it must be 20 amps or less. When we were talking about continuous loads earlier, that would be a load that operates for 3 hours or more at any time. So if it turns on and it runs for 3 hours or more at any point during the day or the week, that would be a continuous load circuit. So remember, when we talked about continuous loads earlier, we're talking about calculating that load calculating the circuit at 80% of its normal capacity. So in other words, we're calculating the load at 125%. And that would be for any circuit that is on for an extended period of time, 3 hours or more at any time. So as an example, if we calculated the total wattage of the lights in our classroom at 1700, when we flip the lights on, it's drawing 1700 watts. We've added up all the luminaires in our classroom, and that's what we came up with. That 1700 would be multiplied by 1.25 equals 2125. So the way that we would size that circuit would be based on 125%, or basically 25% more than what it actually is, just because it's a continuous load. So we've talked about this a little bit in the past, and this is what I meant by the book sort of gets a little bit redundant sometimes, but repeating some of this stuff is not a bad thing. On a branch circuit, the conductor size is tied to the circuit rating. So just a couple of them that you can commit to memory that are pretty easy to remember. A 15 amp breaker, which is effectively the smallest breaker that we can put in our panel, is going to require a wire size of 14 gauge. So they call that typically 14.2 would be like 14 gauge wire, and there's 2 conductors in that cable plus a ground. So 15 amp, 14.2 wire typically. 20 amp, you're going to have to go with 12 gauge. Just remember, with wire, like with a lot of things, when we're talking about metal sizes, as the number gets smaller, the metal is actually getting bigger. So 12 gauge wire is thicker than 14 gauge wire. And then if we're going to jump to 30 amps, we're going to be typically using a 10 gauge wire for that. So it basically goes 14, 12, 10 if you're talking about 15, 20, or 30 amps. So this slide is just breaking down a couple of different types and sizes of wire that we're going to use, conductors that we're going to use on a few circuits. The type NMB cable, also known as Romex commonly, is the most widely used wiring method in the residential dwellings. So we've probably all at one time or another seen this. It's basically an outer sheathing covering up 2 or more conductors inside of it, plus a ground wire typically. So NM cable must have 194 degrees Fahrenheit insulation rating, and that's designated by a B on the cable sheath. As mentioned previously, number 12 or 14 wire are going to be used for the lighting or the receptacle circuits. And then when we get down to the 10 gauge, we're talking about electric water heaters, those 30 amp things. And then the slash and the number after it is the number of actual conductors contained in that cable. So 10-2 would have 2 number 10 conductors plus probably a ground as well. So that little number doesn't include that unsheathed ground wire. So just going back one slide, something I I sort of skipped over and missed, I want to mention the ampacity of a conductor, that is the wire, can be larger than the circuit rating, but not smaller. So in other words, if we are going to run a 15 amp breaker, we can certainly run larger wire than that overcurrent protection is, protecting for. We can oversize the wire if we want to. In other words, we can run 10 gauge or 12 gauge wire from a 15 amp breaker. We just can't run a smaller wire. So in other words, we can't run, for example, a 14 gauge wire off of a 30 amp breaker. I think for obvious reasons, right? The breaker will not trip before the wire is overloaded and hot and potentially starting a fire. A few obvious things about switches and receptacles. They must be sized to match the load that they control. So at the end of the circuit, at the actual outlet where we're going to put the receptacle in, that receptacle itself also needs to be rated for the amperage of the circuit. So if you're running a 20 amp circuit, you cannot connect a 15 amp receptacle to it. Same thing is true for the lighting fixture. And not surprisingly, the same thing is true for the switches that you put in that circuit as well. So everything connected to a 20 amp circuit must be rated for at least 20 amps. And then finally, the overcurrent protection itself must be rated for the expected load. So if we're expecting to draw 20 amps, that all starts at the circuit breaker, and then everything connected to it also needs to be rated for that. When we have multiple panels and we're sort of trying to divide up a large load into smaller pieces, we call that conductor a feeder. And it's a higher gauge cable, obviously. It's a very thick wire because it has to carry a lot of amperage. But we would run that from the service equipment, whatever that happens to be in the building, to a second panel board or sub panel, and the branch circuits are going to distribute the power from those sub panels to the individual outlets within that space. In an apartment building is a good example where an electrical system is going to have multiple meters so that we can figure out and charge people for the amount of electricity that they use only. And so that equipment would branch out from that equipment out to the individual sub panels, and each apartment would probably have its own panel within it to control the individual circuits in that space. Between the service entrance, where it comes in off of the street or up from underground, and the final distribution panel that all the power is going to go to the individual outlets, you may have switchboards or panel boards, and these are just sort of intermediate devices that are going to help divide up that electricity and route it to the smaller control panels throughout the building. A power distribution panel board feeds other panel boards called sub-panel boards, so you really can kind of break this thing up into multiple pieces. As we had discussed previously, it sometimes makes sense to run a single cable over to a panel board rather than trying to extend all those little circuits really long distances throughout your building. So the total amount of service equipment, the capacity of the service equipment, and the amount of electricity brought into a building is going to be based on code requirements, calculations based on that the electrical engineer came up with based on, again, all of the equipment, all of the expected things we're going to be plugging in, the various draws we're going to have regularly or intermittently. All of that just sort of needs to go into a big calculation and sum it all up so that at any given time, that panel is going to be able to supply all of the required electricity. So it all starts at the service entrance equipment and just sort of branches out to various other pieces of equipment from there. Depending on the size of the installation, the size of the building, you might have up to 6 service disconnects per service. And then in large installations where more than 6 switches could be used, a single main service disconnect must be provided to disconnect the power to the building so we can just shut everything off at once. The idea there, I think, is more than 6 is just going to take too long to shut off all the individual ones in the case of an emergency. So one single switch would sort of run those individual switches. So you can either shut off one portion of the building or the whole thing all at once with that single switch. The conductor sizes for the various pieces of equipment, those conductors coming into the building, the ones that are feeding right off of the transformer, need to be sized fairly large. And so you can see the different sizes that we have here. If you have a 100 amp panel, for example, the total for your whole building is 100 amps. That's pretty small. You would use a number 2 AWG. If it's aluminum, you can use a number 4 if it's copper. Obviously, copper has a little bit better conductivity, so we can use a smaller cable when it's copper. So just give you a feeling for, what is the size, what is the diameter of this wire. AWG 2/0, for example, is 0.364 inches in diameter. So that's like 3/8 of an inch thick. That's some really, really thick wire. Even AWG 4 is really large. That is 0.20 inches, so just under a quarter of an inch. Transformers for a residence are typically going to be located either on the ground, if it's an underground system, or up on a pole if it's coming from overhead. But transformers in a larger installation, like a commercial building, like our school, that power is going to be fed right into a transformer that's going to be located on site, so right adjacent to the building. There, of course, are different types of transformers, and this is talking about a few of them, YY or Delta Delta or Delta Y. We're not going to dig into all of the details of what all of that means, but just understand that not all transformers are exactly the same, and they don't all produce the same type of power. Okay, let's bring it back to something a little more relatable. The NEC, the National Electric Code, has required tamper-resistant receptacles to be installed in all 125 volt, 15 and 20 amp electrical receptacles in hospitals, pediatric areas for nearly 3 decades. Okay, so this has been around for quite a while. Tamper-resistant just means that there's something in there, inside the slots of the receptacle, that prevent poking something into that slot unless both slots are being engaged at the exact same time. So in other words, it's not going to allow you to stick a needle into one of the sockets. However, if you happen to have a fork that has the same shape as a receptacle, you could certainly bypass that tamper-resistant mechanism inside that receptacle. But the idea is to keep kids from hurting themselves, because kids are notoriously curious, and when they see something shaped a certain way, they think, oh, well, that's going to fit right there. It would be really easy on an older style non-tamper resistant receptacle to electrocute yourself by just poking a little piece of metal into one of those slots. So these things have been required in certain circumstances, but these are getting more and more prevalent in residential applications now. So recently the NEC mandated that for all 125 volt, 15 and 20 amp electrical receptacles in new residential construction be tamper-resistant receptacles. Now, it's not clear to me whether that means a remodel. I assume that yes, if you're doing any kind of construction, even if it's not a new building, that you would need to, if you're going to install new receptacles, they should be tamper-resistant. I think it just makes good sense also because the cost difference between a TR-rated receptacle and a standard one is not that much. So ground fault circuit interruption protection, introduced in '73 for all outdoor outlets that are within 6.5 feet of the ground. And that made sense because, it'd be pretty easy in a rainstorm to electrocute yourself. So we protect against that by constantly, the GFCI device constantly monitors the amount of electricity going out and coming back, and it detects leaks and shuts off if it detects one. In residential installations, now GFCI protection is required at all 125 volt, single phase 15 amp, 20 amp outlets in the locations listed below, which are not listed below in this slide, but on the book, it definitely takes a look at all the different applications there. So over here in the right column on page 685, you can see that a number of things are listed here. We'll just go through a few. So still outdoor convenience outlets within 6.5 feet. Also now bathroom convenience outlets, that happened in '75. Readily accessible convenience outlets in garages, 1978, but not necessarily pertaining to things that are sort of out of reach, like an overhead door opener or a freezer. Convenience outlets within 6 feet of a kitchen sink, that's interesting, but not necessarily things serving fixed appliances. So we just basically don't want to be able to drop, say, a toaster into your sink, right? And the 6 feet is probably just because of the average length of a cord on an appliance. Convenience outlets in unfinished basements and crawl spaces except laundry. And then convenience outlets within 6 feet of laundry, utility room, or wet bar sink. So this is likely not all of the current requirements for GFCI because just recently I was talking with one of our electrical folks here, and they let me know that GFCI protection is actually required in pretty much all outlets now. Another way to say that is it's required in so many outlets it almost doesn't make sense to run non-GFCI protected outlets anywhere. This basement I'm working on right now, we're going to run all GFCI and AFCI breakers so that the entire circuit, everything connected to any circuit in that space, is going to be protected for both GFCI and AFCI protection. So if that trend continues, and I expect it probably will, it just kind of makes sense, we're basically going to start moving away from what is protected or what is required to be protected with GFCI to what isn't, because it would be easier to list. So in 2002, the NEC required AFCI, and just as a reminder, GFCI is protecting about ground faults. So when the electricity leaks out, for example, into a person, it's going to trip. An AFCI protected circuit is arc fault, circuit interruption. And that's when it's similar, but it's to prevent the electricity from jumping across to a ground. If there's, for example, a cut in the wire that is undetected, or a screw goes into it or something like that during drywall installation, if you get an arc going across, it's just another type of leak, sort of, but it's in an effort to prevent fire from that spark. So if an arc fault is protected, that circuit will also shut off. But these are required in all bedroom circuits in new residential construction, and I suspect that is just going to continue to expand just like the GFCI requirements. Under section 1912, it starts talking about electrical system design. And as with most things in design, it's going to start with a preliminary design, which involves collecting information. In the architectural realm, we call this the programming stage, but something similar happens when the electrical engineer, whoever is in charge of the electrical design, sits down with the building owner and determines all of the various needs. Now, as with designing buildings, oftentimes the people that are being interviewed don't really know kind of what they don't know, right? So the equipment that is likely going to be required that the building owner wouldn't even know about should be well understood by the engineer before we start having that conversation. But the owner is going to be able to inform on a lot of things. They are going to be aware of a lot of the requirements that they have. And so that interview process needs to take place in addition to just understanding all of the basic requirements of a building and all the codes that the engineer needs to follow. The electrical engineer will also have to work hand in glove with the architect and perhaps even the HVAC and mechanical folks, structural engineers, just to make sure that all of the things that are necessary for all of the equipment that's going to go into the building is accounted for. And then, of course, it's always good to ask the question about the possibility of future expansion. If we size our main electrical system for just what we need today, even if we know we're going to expand and put a big addition onto this thing in 10 years, it's generally not a good idea. So we want to make sure that we're accommodating to the extent possible and to the extent that's affordable all the future expansion that might be necessary. And so once a general idea or a pretty clear idea of the electrical requirements are understood by that engineer, they would be typically understood as the best person to talk to the electrical company to describe all of those needs. Because there are so many possibilities in terms of the way we can solve an electrical problem, a good designer achieves the solution by observing and evaluating existing installations, if it's an addition, for example, and adapting them to meet the project requirements. 2, applying electrical system theory that should be well understood by any electrical engineer. And then, of course, and this probably should be listed first, applying the code requirements. That's where it all starts. Everything trickles down from there. So the book goes into a fairly extensive discussion about all of these different spaces. And this is kind of a good way, I think, to break it down when you're doing the design. Sorry about that, I didn't have the display up. Here we go. So these various areas are kind of a good way to break down, I think, when we're pulling design together. You can kind of think of these spaces as individual spaces. That's not to say that each one of these spaces is going to require its own circuit, both for outlets and or lighting. There are a lot of cases where a single space does require dedicated outlets. One of them is a kitchen, and you're going to need probably at least 2 dedicated outlets for the receptacles in there. Another one is a laundry room. So in addition to the dedicated outlet required for a clothes dryer, you would also require all of the receptacles or convenience outlets in that space to be on our own circuit as well. And there are other examples of that, those individual dedicated circuits for a specific area. But most of these can share their outlets and or lighting with the other spaces. But as mentioned, the book goes into a fairly in-depth discussion about each one of these spaces. So I'd encourage you all to kind of go through and just take a look, at least a cursory glance, at the things that you would want to consider for each of these spaces. So that concludes the official lecture portion of this chapter. There is one additional thing I'd like to do before we call this chapter complete, and that is to go through the design example. It is fairly extensive, but we're going to take sort of a quick walk through it. We're not going to go into it super deep, but I do at least want to give everybody a sense of what's involved in putting something like this together. So let's step through this design example. This is starting on page 689, section 1913, and it's talking about an example of a system design of a house that is roughly 61 feet by 36, single story, single family. And the residence contains all the normal things we would expect, lighting and receptacles, and then equipment and appliances including what follows. So we have a water heater, a clothes dryer, dishwasher, a range, waste disposal, and you can see all of these things have the volt amp rating, also known as the wattage rating for each of the appliances, and then air conditioner, garage door opener. Loads are used from the manufacturer's data. So they actually are not, in this example, using something off of a table that is just generic. They're actually going right to the specific equipment that is specified for this project. So in the circuit design, we're going to start by actually working with a floor plan, and we're going to be laying out the location for things like receptacles, switches, and lights. Just a few code issues to talk about. I'm going to switch to this floor plan just real quick. When we're laying out outlets, we need to make sure that every wall section that is 3 feet or longer has an outlet. Another requirement is that no 2 outlets on a single run of wall can be farther than 12 feet apart. The idea there is that if you have an appliance with a 6-foot cord, you could reach any point along the wall with that appliance. In a kitchen, the maximum distance between outlets is 3 feet, and then any dedicated circuit to a piece of equipment that is a sort of a higher voltage, like a clothes dryer, is going to have its own dedicated outlet. But that's kind of it. That's kind of the main rules that we have to talk about in addition to the AFCI, GFCI stuff. The next step would be to connect all of the larger appliances. Clothes dryers we've talked about. We also have to remember that most houses are going to have some type of air movement system, like a furnace or an air conditioner. Those are some pretty heavy draw items as well, especially AC, and so that needs to be accommodated as well, and there has to be specific ways that we're going to wire that in. But in most cases, most applications, we're just talking about a plug of various types and sizing the circuit accordingly to the draw. Next, of course, you want to think about the lighting fixtures. And in the olden days, we didn't necessarily put lighting fixtures directly in our ceilings. We just had switched outlets. Nowadays, most places are going to have some type of lighting fixtures in every room. But the specific design really needs to be coordinated with the homeowner, giving them the amount and the types of lighting that they want throughout every space. We also need to think about the switch types that we're going to use. There are a lot of different switches on the market now. Some of them are just your standard flip switch. We also have panel type switches. Now we have switches that are smart, right? So that they can be operated manually or by talking to a smart device like Alexa. And we have light switches that are motion activated or even heat sensitive, so that when someone enters the room, they come on automatically. As far as the light fixtures, we used to be really big into the can lights, and the can lights were this large recessed area that went into the ceiling. And nowadays, now that we've sort of switched away from incandescent and even CFL bulbs, which take up quite a bit more room, we really have made a transition in recent years to the LED light types, and those are quite a bit thinner and they take way less electricity than conventional light bulb. And so these things are actually, we're able to put quite a few more on a circuit. For example, a 100-watt light bulb in an incandescent type only requires about 15 watts in an LED bulb. So as you can tell, that sort of upends the whole circuit design in terms of the lighting circuits, because we can really run a lot of lights off of that single circuit. So the fixtures need to be decided on, both in terms of how they're going to get installed and then what the rating for each individual light will be. And then of course the switches need to be located. And remembering that switches, there are a few guidelines as to where we must put switches. In a stairway, we have to have a switch that controls the lighting of the stairway, both at the top and the bottom, easily accessible from the top or bottom, so that you never have to walk the stairs in the dark. On a hallway with any significant length, we also need a light switch at each end of the hallway so that we can turn it on regardless of which direction we're traveling through it. In terms of just a standard switch in a room, we typically are going to put that on the wall right next to the entry into the room. So for example, in this bedroom number 3 down here, as you can see, there's a switch right inside the door. We don't want to put the switch on the swing side of the door. We always want to put it opposite the hinge side of the door so that when the door is open, we can access it easily without having to reach behind the door. So that's just something that a lot of times gets overlooked. We don't really think about it always, but that switch needs to be placed on the latch side of the door, right inside. Some thought should be given to larger spaces and all the different possible ways that we might want to turn a light on. For example, in this family room, there's an entry coming off of what looks like a deck here, so you have a switch there to kind of control the family room lights. You also have one just inside of each of these 2 doorways. So depending on which direction you're coming from, there's a nice convenient way to flip that switch on. In a lot of cases, those switches are going to be located near doorways. We also have to think about where we're going to place switches for devices like a garbage disposal in a kitchen. That switch should be placed in a convenient location. Sometimes the sink is on an island, so we have to get innovative about where we're going to place that switch because we don't have a wall typically on an island. So sometimes they'll have to be just put underneath the countertop inside the cupboard or something like that. You'll notice that bedroom 3 is indicating a light inside the walk-in closet here, but there's no switch associated with it. So when you see that, that's either an omission, someone forgot to put something on there, or possibly that light is is on a smart switch. It's just constantly powered, and we can either turn that on and off with a smart device or possibly even a motion detector device. But in either case, we really should, I would consider this a mistake, we really should be indicating how that thing comes on, regardless of whether it's a manual switch or a smart switch or a motion activated switch. If we are going to use a standard switch in this type of a scenario, that switch can either go on the inside or the outside of the closet. Most commonly, probably it's on the inside of the closet. So you can just sort of open that door, reach in and flip that switch on. And again, even if it is not on the side that the door swings, we still want to put it on the latch side typically. When we're doing a switched circuit based on 3 different switches, remember that the 2 switches that are at the far end of the circuit opposite each other are going to be 3-way switches. The one in the middle is going to be a 4-way switch. Typically outdoor lights are going to be switched at the door that leads closest to the light that's outside. If you have a scenario where you have a lot of lights around your house, perhaps they're in the soffit or something like that, again, that switch is going to be controlled typically near the front door. At the back of the house, you can see we have a couple of additional exterior lights, and each one of those is controlled with a switch that's fairly nearby. Typically, we're going to put those switches nearest to the part of the door that's going to open. And then finally, we want to give plenty of thought to how the switching is going to work in a bathroom. When you have a bathroom, you have a number of different possibilities. One, you're going to have a fan. The question is, do you want that fan to come on every time you turn on the light? So would those be wired together? Or would the fan and the light have a separate switch? Also, are you going to have a separate light over your tub or shower? And should that one be tied in with the fan? So you just got to kind of think through how the building owner wants to sort of interact with their lighting and their fan system in their bathrooms. Number 5 on this list is talking about where do we place the panel board. The panel board is pretty much going to be governed by where the drop is going to be. So we really want to try to put that in a place that is the most convenient for the homeowner, but also doesn't add unnecessary cost. A lot of times that means putting it on an exterior wall closest to the drop or closest to the utility. The panel board should also be located in a spot that can be left clear. We can't by code put anything in front of a panel board, a breaker box, if you want to call it that. So the location needs to be in a spot where you're not going to store things, you're not going to build anything up in front of it. And then finally, we're just going to run the circuits to all of these things. And we want to make sure that we're thinking through how we're going to divide the circuits up. For example, in a lot of cases, the most economical way to run your wiring is to group your circuits by area. So in other words, in a bedroom, you might run the lights and the outlets and anything else in that area off of the same circuit. Other folks, though, don't mind spending the extra money to separate the lighting circuits from the electrical circuits. And this is sort of a convenience thing, especially if you've ever had to find the breaker box if you trip a breaker. If you trip a breaker in a situation like the first one I described, the lights go out too, right? But if you're concerned about tripping a breaker, or if you're concerned about tripping a GFI or an AFCI, and you want to make sure the lights stay on in that scenario, the entire lighting circuit could be separated. So just thinking through how you want all that to be wired together, both in terms of cost, of course, but also in terms of convenience, is an important step. And then we want to think about how that's going to be laid out within the panel itself, how we want to arrange all those individual circuits. So it's not really necessary to organize things, but if you want to put, for example, all of your lighting circuits, the breakers for those all in one area, and then below that maybe you do your power and then you do your kind of high voltage stuff in another area, sometimes it's easier to find those breakers when it comes time to turning things off or tripping them back on. So this configuration is kind of showing how that circuit arrangement might look on a plan. And you can see that this one is actually tying the electrical into the lighting circuits, right? So in this scenario, let's just look at this bedroom number 1 up here. You can see that the panel, or the panel is fed from circuit 6 and 8 going into this exterior outlet. And it looks like it then, it looks like it's tied into this one adjacent to it, but it is not. If we follow this bedroom 1 circuit all the way back, you can see that it sort of terminates at this outlet. I'm not sure why they jumped across from this one over to the switch. I think I would have just fed it right off of this one, but regardless, let's follow the circuit back. If we come up across bedroom 2, you can see that it connects here, comes down, jumps over to bedroom 2 from 1. It comes up around, and then at this outlet right here is where it terminates and goes back to the panel. So you can see this is connecting to circuit 21 because we see the arrow right there. So Another way to think about that is it comes across from the panel board, which is in the garage, starts at this outlet right here, circles around, and picks up all of these, including the light in bedroom 1 and the light in bedroom 2. You can see it's jumping across here as well. So you can spend more time just kind of analyzing this particular plan, but this is basically what needs to be shown. We can look at this pretty easily as a contractor and understand how the designer intends for this thing to be wired. Even though we're not necessarily dictating exactly where those wires run, we know that each circuit is going to run a certain number of outlets and switches and lights based on this diagram. The remaining sections in this chapter go into the load computations, and we're going to kind of pause here and not dig into that as deeply, but take a moment and look through this stuff and just at least give it a cursory glance on the types of things that we're going to be looking at and how we're going to go about calculating those loads. On a simple residential installation, these calculations may or may not be necessary because in a lot of cases you're going to be way over on the amperage supply that you need on a given circuit. But in cases where it's a very large type of an installation, getting in and digging out the exact calculations for all of these things is necessary. So just real quick, number 1 is talking about calculating the general lighting load. We move on to the appliance and laundry circuit load. And remember, all of the values that we're using for each of these calculations is voltamps, also known as watts. Continues on to number 5, determining the appliance and equipment load. And then it goes on to talk about the service entrance design. So this is where we calculate all of the loads to kind of figure out what size panel we need in this residence. Just remember, if you come up to a maximum that is very close to the capacity of one size, you may consider going to the next size panel just to account for future expansion. The chapter finishes up by going through a calculation for circuit design and then finally panel board selection. So in summary, what we're looking at doing with this is not only working out a layout that is code compliant, applies with all of the NEC requirements, but also fits all the needs of the ultimate people that are going to be using the building, and hopefully gives them the convenience and the service that they need, at the same time as making sure that the circuits are sized accordingly to the load that they're going to be on so that it's not tripping all the time, and we're getting a good sign off on the inspection from the electrical inspector that's going to approve the design and the installation. Reach out if you have any questions. Please take your time with the quiz, and we'll see everybody next time in class.